All right. Today is the last day of new material for the semester. Yay. Just as, You're looking at me like you're shocked. Do you want more? I can make, yay. All right. Next week is review, just as a little schedule. Tuesday, review. Thursday of next week is test 3. Then comes Thanksgiving week. I know. If we can all survive to that week, we're good. Following week is Dead Week. There will be classes for the Dead Week. The Tuesday, Thursday lectures are review. The Friday Bishop Hall tutorial.
Is that our last problem set?
Yes. So that, hold on. The Friday Bishop Hall tutorial will be the final review. And then you have finals next week, and you can look those up. They're also listed in the syllabus. The last homework, problem set 11. Will be turned in on the day of the review or after the review. So this week review, and then, or this week new material, next week review, and then test 3, Thanksgiving week, and then Dead Week, we'll just have reviews. Just so you know, the final, well, let's compare briefly what's a test. A test is 25 multiple choice, 1 appetizer problem, and 3 15-point problems. A final, a test can either be 15, 20, or 25% of your total grade. A final is 30%. Tests run an hour to an hour 15. And has 100 points total. A final is 50 multiple choice, 2 appetizer problems, 6 15-point problems, 3 hours, and for a total of 200 points. So one of the reasons why I've kind of enjoyed having the tests last an hour and 15 minutes is it's not a big step to go from an hour 15 to 3 hours. I've had semesters before. I've taught Monday, Wednesday, Friday classes where their tests are only 50 minutes, and we all know in reality they're more like 45. With a 5-minute get out of here. And then they walk into a 3-hour final, and it's a bit of a marathon. To go from a 50-minute test to a 3-hour final is a big slog. So that's why I enjoy these hour to hour 15-minute tests, just so you get the feel for what a final is. A final tends to be, or a final is comprehensive, and a final will be 1/3 test 1 material, 1/3 test 2 material, 1/3 test 3 material. So you'll get 2 15-point problems from each of the 3 test materials. It will be comprehensive exam. As we get closer to the final, I'll get a better feel for what's going to be on the test and what's not. One of the things that you will know, it will be on the test, is alpha will equal 0 for the rotation. Because you got one where alpha wasn't 0 on the rotation. We'll talk about the final later. But as for test 3, fluids, sound, and really those are the big, and statics, namely stuff like that. On Blackboard, the test 3 packs from summer 16 and summer 15 are up. So you can start looking through those. Give you guys the weekend, and then on Tuesday we'll go through. What we'll do is Tuesday, the AM class will get one version of the 16, and then the PM will get one version of the 15, so that there will be a full recorded video of both versions going on. So you'll have a full set. Hopefully by then I'll just do all the answers for the ones that we don't do, and we'll be fine.
You said it's already on Blackboard? Or
Mhm.
Blackboard?
It's on Blackboard already. Trying to think of other stuff. Also, if you're interested in test reviews for the last couple of years, go into the Google Drive, look into various semesters, and you can see T1 review, T2 review, etc. So let's go into the new material. This should be fairly quick. One of the things that we talk about, Doppler shifting. In your experience or experiences day to day, the most noticeable case of Doppler shifting is like when a car comes at you and it passes you, you hear that woo, that shift in tone. And really what's happening, if you're standing still and here's your car, that's like the sound. The car is moving with the sound waves. Now granted, it's not moving that quickly with the sound waves, but I just wanted to exaggerate at the point. So the waves are kind of bunching up on the front end, the end in which it's moving, and it's kind of backing away from the ones where it is moving away, because it's like it emits that one, moves to the left. That one is moving to the right. It emits another one, moves to the left. That one's still moving to the right. And it's a lot like if you're on the back of a ship and you're throwing objects off the back of the ship. The apparent distance between those objects are further apart than they would if you were moving forward the ship. If you were moving with the ship, they would kind of bunch up. So on that side, as the car has passed you, now you're hearing the back end, the one where the waves are further apart. So these, your brain interprets it as high pitch. These, your brain interprets as low pitch. And for Doppler shifting like this, it is for a moving source. Now, one of the things that you have to be aware of when you're doing Doppler shifting problems is, what is the source doing? Is the source moving or is the source standing still? If the source is moving, you use these equations. Now, Vs is the speed of sound in air. And like I have said before, outside of the lab, in this room, on all problem sets, on all tests, on the final, the velocity of sound in air will be 350 meters per second. And why is that? Because when I write these problems, I take the time to make sure that the numbers work out right, and it's a lot easier to get 350 to agree with the problem than it is to get 343 or 3 whatever with the problem. Now, one of the things that we're going to have to ask ourselves, and this is, I'm going to go through this painfully slow because it was painful when I had to learn it. If you have a moving source, that part 1 plus or minus V over Vs is in the denominator. Now there is a reason why. There's a derivation, but we don't do derivations in 213 all that much. So we're going to go with the time-honored tradition of because I say so. It just makes things easier. So one of the things that we're now going to do is we're going to use our brains to figure out, is it the one on the left if the object is coming at you, or is it the one on the right where the object is coming at you? So let's just talk about what we hear. If a car is coming at you, do you hear a higher pitch or a lower pitch? Higher. And if it goes away from you, do you hear a higher pitch or a lower pitch? Lower. It'd be kind of freaky if it was higher and then higher still. In the denominator, if you want f prime to be a bigger number than f, the denominator must be a bigger number or a smaller number? Must be a smaller number. So if the number is less than 1, a number less than 1 in the denominator will produce a number bigger in the end. If you want that number, what did I say, smaller? If you want that number to be smaller, then the denominator has to be bigger. So bigger denominators will produce smaller f primes. Smaller denominators will produce bigger f primes. So which denominator produces a small number? 1 minus something or 1 plus something? 1 minus. 1 minus will produce a smaller number. Now, actually, let me write some notes with this because we're all starting to get confused.
For every prime.
Oh, huh? All right.
Yeah.
Let's dial it. Let's pump brakes a little bit. We're all getting confused. Say I want f prime to be bigger than f. That the frequency that I hear is bigger than the frequency emitted. So in order to get f prime to be bigger than f, the denominator must it be less than 1 or greater than 1? It has to be less than 1. A number less than 1 in the denominator will show that f prime is greater than f. Which one of these is guaranteed to produce a number less than 1? This one. So for sources moving towards you, the frequency that you hear is equal to f over 1 minus v over vs. Now, you could just pick the other one and figure it out. Any number that this thing cranks out, f prime will be less than f. You'll get a lower frequency. So sources moving away from you, f prime equals f over 1 plus v over vs. And so those are the two. And that's how I typically reason it out. If it's a moving source, the 1 plus or minus v over vs is in the denominator. If it's moving at you, you use minus. If it's moving away from you, you use plus. Also, you know that moving towards you, you're going to get a higher number. Moving away from you, you're going to get a lower number. In addition to moving sources, there are moving observers. As in point, think about like a train station with the whistle. You're on your little train. The sound waves with respect to the train station are the same distance apart. But the good analogy that I have for something like this is if you're surfing and the waves are coming at you at a regular rate and you swim into the direction of the waves, you're encountering those waves more quickly. The frequency is higher. If you're moving with the waves are overcoming you at a less rate. So if you're going against the waves, you get a higher frequency. If you're going with the waves, you get a lower frequency. And so that's an analogy from surfing. Moving observers, that 1 plus or minus v over vs is in the numerator. So the equations that we deal with, those parts will be in the numerator. So f prime is equal to f 1 plus v over vs F prime F 1 minus V over Vs. So which one will always produce higher F primes? This equation or this equation? The one on the left, because 1 plus something will give you a number greater than 1. Yes.
What's the middle picture supposed to be? Like, what is that illustration?
Oh, this? That's my picture of a train station with the bell. That's a little bell with the little bell thing. And it's... So that's the Oxford train station with the little bell thing. Don't make fun of my train station.
It's okay, I just wanted to know what it symbolized. So that
It symbolizes a sound source. Okay. I know you're not judging. It's okay.
I can't draw, so.
I know, neither can I, so. I mean, this is a picture of my train, so.
Oh, okay.
It's a train. Oh, now people are. You were being very polite. Thank
You
you.
said it's surfboard though, so I was
Very impressed.
yeah.
The picture is very good.
Oh, thank you. Now that PM class has been canceled, this is kind of like a day off in school or something. More relaxed. So this one is observer moving towards source, and this is observer moving away from source. Now, the one thing that we're definitely not going to do is we're not going to move supersonic. We're not going to move with a velocity greater than the speed of sound, because that gets weird. So if we had just kind of a cheat sheet of moving source, moving observer, hold on, can't spell. Observer towards and away. Moving source F prime, F prime, F prime, F prime. With a moving source, that part is in the denominator, 1 V over Vs, 1 V over Vs, frequency, frequency. If you're moving towards the source, you're going to hear a higher pitch. That means that must be negative. If you're moving away, you're going to hear a lower pitch, which means you got to have a bigger denominator, which means you plus. For moving observer, that bizarre chunk of code is in the numerator. 1 V over Vs, 1 V over Vs. If observer is moving towards, you're going to hear a higher frequency. The only way to hear a higher frequency is to make the numerator higher, so there's a plus. For observer moving away, you do a minus sign. So that's the cheat sheet that you'll get. Now, you won't have these, you'll just get those 4 equations. And it is up to you to know which one represents which equation.
So really there's an imaginary one under the observers.
There is only what?
Under the observers is really an imaginary one.
Only under observer?
No, under the observers. Because it's in the numerator, it's an imaginary 1. That's what you're saying, right?
There's no imaginary 1. We'll talk after. Let's do a simple example. A police car is passing by, and it has a velocity of actually 30 meters per second. You hear a frequency of 600 hertz. The first question, what is the frequency of the car? And as the car has passed you, all right, and then what is the frequency that you hear going away? Now sometimes we write subscripts A and T, A for away, T for towards. So for something like this, I've got a moving source. This part, it's definitely moving towards. So F prime is equal to F over 1 minus V over Vs. I know what V is, 30. I know what Vs, 350. Vs will always be 350. I'm looking for, what am I looking for? F. So F prime, 1 minus V over Vs is F. F prime, it's what I hear, 600. 1 minus 30 over 350. So the frequency of the siren (548.6 hertz). And so that's the frequency of the car coming at me. Now, as it goes away, you're going to hear a different frequency, a frequency that's lower. Now that it's a source moving away, F prime is equal to F over 1 plus V over Vs. F is 548.6. 1 plus V, 30, 350. Yes?
So that equation is for the frequency going towards the observer?
Mm-hmm. And notice that I use this one because now the car is past the observer, so it's a source moving away. And so you hear 505.3 hertz as it passes. All right. Now another simple example. We'll do a little bit of a hybrid for this. You're on your little train. Let's see. The train station is emitting a source of, you can't tell, but what you can hear is a 700 hertz whistle. The velocity of your little train is 80 meters per second. So the first part of the question is, well, what's the frequency of the source? Well, it's a moving source. No, it's not. It's a moving observer. It's moving observer towards, so F prime is equal to F1 minus, or 1 plus V over Vs. All right, slow it down even further. It's a moving observer. The 1 plus or minus is in the numerator. It's towards, so we're going to hear a higher number, so it has to be a plus. I'm looking for F. So F prime over 1 plus V over Vs is that frequency. F prime 700. 1 plus V 80 over 350. Yes?
If it's moving towards the source, why is it not plus?
Why is it not minus? Is that your question? Because that's not the type of equation that we use. If that was a minus, where's my, if that equation was a minus, F prime would always be a lower number. But you know that because you're heading towards each other, you should hear a higher frequency. So if it's if the 1 plus or minus is in the numerator, it has to be a positive. Has to be positive.
So why'd you put in the denominator then, if it's all there?
Why did I put this in the denominator? Well, now I'm starting to do algebra. Because I have to solve for F. And I get 569.8 hertz. And that's the frequency of the source. So now we're going to have a little bit of fun with this. Let's say that the source is a tube open at both ends and is at its second, I gotta kill time somehow, overtone. So the tube emitting at 569.8 hertz is at its second overtone. It's open at both ends. What is its length? So a tube's frequency is this. And you get that. Second overtone is what in? And I'm gonna get a sip of water real quick. 3. Guys. use? What's the value of V? Do I use 350 or do I use 80?
350 or what?
80. It's the velocity of the train moving. And shrugging shoulders is not. 350, that V is. Yes, I leave for 2 minutes and the whole place just turns into Lord of the Flies.
Nobody has tried to kill anybody yet.
I know. There's no pig head in the middle. What's your question?
When did you say the velocity of the train was 80?
Velocity of train was 80. What's that particular V in the frequency definition? It's the speed of sound. So that's 350. What is the value of N? Its second overtone. 3. So hopefully this will be a decent length, 0.92 meters. So that's the length of a pipe if it is at its second overtone and emitting a sound at 569.8. Now that I know that the pipe is emitting, now just roll with it here. The pipe is emitting a tone at 569.8. I plug one of the ends. I want to know the frequency of the second harmonic and third harmonic. So you have a pipe emitting a frequency at 569.8. It has a length of 0.92 meters. You plug one of the ends. What is the frequency of the second harmonic? No, it's the same pipe. I only took the pipe and took a big cork, and so the length of the pipe is still 0.92.
Now you use 2 instead of 3, right?
Well, we're not going to get to that point yet. Give me the trivial answer. Well, that's the equation. Some of you should just freak out when I mention, give me the frequency of the second harmonic. It can't exist. Second harmonics don't, the moment you plug that thing up, the second harmonic goes away. So does not exist. The third harmonic, the frequency is NV over 4L. N is 3, V is 350. That's 4. The L is what we get, 0.92. And I get a frequency of 285.3 hertz. All right, last bit that we could play with this. Yes. If you plug one of the ends, it becomes a half pipe immediately. A pipe open with both ends, it's, how long did I say it was? 0.92 meters. Both are open, so it's a full pipe of 0.92. I plug one of the ends, now it's a half pipe length, 0.92. Correct.
And how do you,
And that's why the 2 goes to a 4 in the equation. NV over 2L goes to NV over 4L. Okay, last thing with this problem before we move on to the last problem. Let's say the string that's fixed at both ends is emitting at 569.8. It has 2 antinodes. So its standing wave looks like this. I'm going to give you the length of the string as 0.8 meters. The mass of the string is 20 grams. What is the tension of the string? String has a frequency of 569.8. The length of the string is 0.8. The mass of the string is 20 grams. What is the tension? Well, the frequency is NV over 2L, and V is a square root of tension over lambda. So frequency becomes NV over 2L, or actually get rid of that V, tension over lambda. Lambda is mass over length, or 1 over lambda is L over M. So this becomes N over 2L TL over M. I'm going to square both sides. F squared, N squared, 4L squared, TL over M. One of the L's cancels. Now 4LM F squared over N squared is equal to T. So we've algebraically solved for tension. I know what the length is. I know what the mass of the string is. I know what the frequency is. What's my value of N? What should my N be? It's 2. You can associate your N value for a string with the number of antinodes. One of the things that will happen on the test well, let's do this first and then I'll talk about the test for a bit. 4 times 0.8, 0.02. Let me get a new sheet of paper. 4 times 0.8 times 0.02 times 569.8 squared, all over 2 squared. And that is equal to T. 2 squared cancels with that 4. And I get a tension of 5195 newtons. Is that a good number? I don't know. It's whatever. It's the number that we get. One of the things that will happen on a test all of these are fixed and all of these are standing waves. We'll start with, well, let me label these. Let's do a quick round of pop quizzes. First harmonic is what? A. A is the first harmonic. This is the first time where I get to say it. Don't look at me, look at the board. It's normally so. C has how many antinodes? 3. Excellent. I have 5 nodes. What am I? D. D is what harmonic? 4. All right, you're now banned from saying anything. Excellent. In the overtone system, D is what? If the silence lasts for 10 seconds, you're allowed to answer. 3, it's the third overtone. What comes before the first overtone? Fundamental frequency, yes. The fundamental frequency is also known as the blank harmonic. First. How many nodes does C have? 4. What is its overtone? It's overtone. It's the second overtone. There are 3 antinodes, which means N is 3. Yes?
How do you know where the nodes are?
The nodes are typically, well, since I've drawn it badly, it's the nodes are where they cross the plane. And then the ends are always nodes as well. They'll be a little bit better labeled on the test. This was one of the things where it was the night before the test I came up with this, and they had never seen this before. And I was like, let's see how we do on the test. And but some actually figured it out. A and B have the same length. Which one has the higher frequency? B. How many nodes are in B? 3. B is the second overtone. True or false? False. What is it? First overtone. All right. You're not allowed to talk, but you can sign.
How do you know which one has the higher frequency?
More waves. Same length, more waves. I would have to say that B and C are of the same frequency because it's the distance between, or the period, the wavelengths are about the same for that. In the test, they'll all be the same length. It's just that I had to just slap this test down real quick. Good. All right, the last problem. Uh-oh, I'm down to... Oh no, I got more paper, yay. Now, I was in a casino a while back, and my mom was asking me, like, what does physics do for me? And I was like, well, physics can do a lot of things. Take a roulette wheel. Now, in the if you were to go to Tunica, go to do they have roulette wheels in Philadelphia down in those casinos? I know they do in Biloxi. You notice that there is a plastic barrier between the bettors and the wheel. You also notice that there are these little diamonds on the wheel. Back in 1972, those things didn't happen. It was more of a smooth wheel, and there wasn't a barrier between the two. And what some enterprising physicists from the University of California at Santa Cruz did is they got a hold of an actual roulette wheel, took it up to their attic, and on their summer break, they played roulette like nobody's business. And they figured this thing out. Now, when the ball is going away from you, you hear a frequency of away. When the ball is on the other side coming at you, you hear a frequency towards of F prime. One of the things that they're unable to figure out immediately, you just can't look at a roulette wheel table and tell how fast is the ball initially going. Now, what they did was, it was some hard grade cheating. What they did is they took an individual, they put his hand in a sling and a cast, so it made it look like he had broken his arm. And he put his arm right at the roulette wheel table, and he was able to record the frequency of the ball as it comes towards him and away. Now, it is a moving source, so away is 1 plus V over Vs, and towards is 1 minus V over Vs. And what this problem does is it opens up a class of problems that I call roulette wheel problems, because of the technique that I'm going to show you right now. These frequencies, they know what, because they can hear it, the frequency of the ball as it goes away, the frequency of the ball as it comes towards. They know the velocity of sound in air because they've got a little thermometer up in the room, and they've done the little equation thing that you guys are going to do next week. So they know the velocity of sound in air, but they don't know the frequency of the ball, the frequency of the ball that it makes. But they don't need that. The two unknowns are the velocity of the ball and the frequency of the ball as it's normally emitting sound. What they did was they took one and divided by the other. It doesn't matter which one. So F 1 plus V over Vs, F 1 minus V over Vs, those cancel. Their goal is to find the velocity of the ball. This is in the denominator of the denominator, so that gets kicked up to the numerator. and we get this. So the algebra that we need in order to extract V is we cross multiply. And we get this. We distribute. And we get that. In fact, there was a whoopsie, 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 whoops. Oh, keep that. It's very important to keep your subscripts. What I'm going to do now is I'm going to move this over here and that over there. And I get this. Now I factor out the V and the VS. And now I solve for V. Now what they had was a very primitive computer in the bottom of their shoe, and it would listen to the frequencies and compute the velocity of the ball is a known quantity. So what good is knowing the initial velocity of the ball? Well, you've got theta equals theta naught plus omega naught t plus 1/2 alpha t squared, and omega equals omega naught plus alpha t. If you've got V naught, you know that, so you know omega. If you know omega, you know that. They were in their attic for like 3 months, figuring out how quickly does a roulette wheel ball drop. Because of that, they knew alpha, and they knew the omega at which it dropped. So if they know omega at which it dropped, they could figure out t. Now I've said before, theta naught is always 0, except in one occasion, and this is it. Wherever the dealer puts the ball down on the table, that's theta naught. So now theta naught is a known. You now know where t is. So now you know where that thing's going to land. Now, for the most part, what they did is they didn't bet specific numbers. They bet sides of the wheel. It was either going to land on that side or the other side. They changed a game where it was 52-48 to the advantage of the dealer to 60 to 70% in advantage of the player. And what does that mean? That means a lot of money. And eventually the casinos figured it out. They went up to the dude with the broken arm and said, if you really wanted a broken arm, we'll oblige you out in the back with a sledgehammer. We encourage you not to come by again. And so they stopped doing these. And this is the reason why. And it was funny because as I was talking to my mom, the roulette wheel dealer's looking at me like I know what I was talking about, because these dimples, which they weren't there before, add a layer of chaos, add a layer of unpredictability to the whole thing, so you couldn't really figure it out. They added this sound barrier so that you couldn't have your broken arm with a microphone inside listening to the Doppler shifting. Also, back in the 1970s, they allowed betting up until the point where the ball dropped down. It used to be like they'd put the ball down and then they'd spin it, and you could still make bets. And once the ball started to bounce around in the middle, the betting was called off. Current rules say once the ball goes in play, betting must stop. Why were all these rules put in place? Physics. So, and what ended up happening was they moved out of the gambling industry and went on to Wall Street and made a whole lot more money. All right, that is it. No afternoon class because of the investiture, whatever it is. Tutorial 1 o'clock, Bishop Hall, tomorrow. See you then.
Oh, she better.
What?